Okay, let's get started with lecture number 8. In this one, I'm going to be talking at first about the architecture changes for assignment 3. So like a really quick review of the architecture of assignment 2 in order to introduce the context of why assignment 3 is introducing some new things. I'll be talking about SFML textures and sprites and some basic texture animation that we're going to be doing for assignment 3. Just keep in mind that these slides, I probably should have had a closer look at them. The slides were made for SFML2. And so I know, for example, when you say in SFML2, texture.load animation now is like texture.open animation, or texture.load from file is now texture.open from file. And so there might be some slight syntax changes, but all the theory and stuff is still the same. So I'll try and mention that if I notice something that has changed, I'll post on Brightspace about it. Okay, so the assignment 2 architecture, you're all writing assignment 2 right now, hopefully. You're not waiting till the last minute to do that. So you're aware that we have this sort of game engine object that has all of our game systems there. So all of our systems are part of this one game engine object. And then that game engine has an entity manager which stores the entities, and the entities store components. And I talked a bit last time. I won't go through all the details of this, but our components are just pure data. They're stored in the entity class, and each component has its own class. So this is pretty much going to stay the same for all the assignments in our course. The entity class is also going to stay the same, so I don't need to go into all the details of this other than just to remind you that like the entity stores this tuple of components and a little bit of extra data like the tag, the ID, etc. That's pretty much going to stay the same, as is the entity manager. And the entity manager, again, stores, this is like a factory class. We got some, we implement this delayed add and remove functionality, and we also have a secondary map from tags to entities such that we can now do things like give me all the bullets, for example. The entity manager will also be staying the same for the remainder of the class. The thing that will be changing is the game object that we had before. So the game object basically handled everything for assignment 2 because we just have that one scene of like you start the game and you're immediately playing the game. This is the thing that will be changing. So just keep in mind that before we just had one game object. It's the top level game object. It holds all the game data. All the game systems are there. All the gameplay code is there, etc. We also have this vec2 class, which will not be changing. So the game thing is the thing that will mostly be changing for assignment 3. So this engine, I said all of this is literally the same slides as before, so I won't go through that. But the limitations of this engine were that it could only display one scene, right? So it could only be playing the game. There was nothing else that we could do with this engine. It could not load any texture or sound assets. We're going to be talking about a new assets class that we're going to be creating for assignment 3 and assignment 4 that can actually load textures, sounds, etc. It could not display any textured animations. So what it could do is you could have like a shape, a static shape that was being drawn to the screen, and then you could do things to that shape to sort of mimic some sort of animation, right? Animation, again, doesn't really like exist in a discrete sense. If you've ever watched a movie, it's just like a set of still images that tricks your brain, if it's fast enough, into thinking it's motion. So for assignment 2, the way we did that was by moving things around. So I guess moving something could be technically a form of animation. You're bringing something to life by moving it around, but we also rotated it a little bit. But what I mean here is that like you can't actually display like, you know, the equivalent of like an animated GIF, right? Where you have like Super Mario drawn in a bitmap and a bitmapped animation of showing different frames of animation. That's something that we couldn't do with assignment 2. We didn't have any sort of menu. We did have like IMGUI, which you could use as a menu, but what I mean is an entirely different scene of the game, which could be like an inventory menu or a main menu, etc. And we will be showing how these game scenes can be implemented. I'll be introducing the high-level architecture now, and then when we introduce assignment 3, I'll go through the actual code of how that works. So in assignment 2, again, the game class handled all the functionality for the game. Everything was in that class. Some of the functions will remain the same over all game scenes. So for example, in our game engine, even if we do have different scenes in the game, some things will always be the same. Like, we'll always have the same window. We might always have the same config file. We might always have the same assets or main loop structure. But some of the functionality will be specific to the type of game scene that's currently shown. So for example, the input controls, they're going to do different things whether we're on a menu scene or a battle scene or like an overworld map scene. Those inputs that we give are going to be different. Maybe some of our rendering is going to be different. Maybe we have special textures or shaders or whatever. It's happening on the menu scene that we wouldn't have somewhere else. The game logic, maybe collisions on the world map are different from collisions in the battle scene or whatever. So we can identify, okay, our games as they get more complex might want to have different logic, different systems, different rendering, different input based on these different scenes. So how are we going to handle that? Well, in assignment 2, where we had this one game class that did everything, now we're going to separate that into a game engine class that handles the more low-level stuff that is shared amongst all the scenes. And then we're going to have a scene class, and the derived scene classes are going to handle that. So let's separate the previous game class into two types of classes which handle this new functionality. So the game engine class is going to have all the functionality that's present in all the scenes. It's going to construct and manage all of those scene objects. And it's going to handle the running and the quitting of the game. And also, I don't have a note here, but like all of the input handling from the user. So whether the user has clicked the mouse or pressed a key on the keyboard, it's going to handle all that as well. The scene class is going to handle functionality that's specific to those scenes, and it's also, each scene is going to have its own entity manager, because we don't necessarily want to share all the different entities between scenes. Like, since our rendering loop for our game class or our scenes is just going to draw all the entities, you don't necessarily want to draw all the entities of the main game in the menu or something like that. So each of these scenes is going to have its own entity manager as well. And before, I was started off the course by sort of trash talking object-oriented programming. But again, remember, that was like object-oriented game design programming, right? So that meant the handling of the entities, etc. But here, we will be using object-oriented programming to help us manage scenes. So we will have a base class scene, and then some derived classes which implement different scene functionality. But that is not the same thing as like the object-oriented design. So OOP still has a place in our game engine, just not in the overall design of how we handle entities and gameplay mechanics. So what's going to change in this new game engine class? Well, over here we can see some new variables. So the game engine class is going to store sort of the top-level game data that is really relevant to everything. So no matter which scene is playing, this is the stuff that needs to be managed. So for example, the assets, right? All of the different textures and sounds and stuff that we load from files, those are always going to be present in the game engine class. The window that we're drawing things to. Now, I guess you could envision a game in which you have multiple different windows open, and maybe you interact with different windows somehow. That could happen. But for our games in this class, we're just going to have a single window, and they're all going to be drawn, all of our different scenes are all going to be drawn to that window. And also, it's going to manage the different scenes. It's going to perform that sort of high-level functionality, for example, of the changing of scenes. So which scene is playing when you start the game? How are you going to actually change from one scene to another scene? It's also going to handle the input. Its run function is going to be the main game loop. And within that game loop, we're going to see that, okay, it's going to handle all this top level stuff, and then it's going to say, hey, scene, whatever current scene is playing, you do all of your logic now. So that'll just be one of the parts of the main game loop. And then the game engine pointer will be passed to the scenes in its constructor. So the scene will also have a reference to the game engine. Now, I haven't decided yet for assignment 3 whether I'm going to do this or introduce the game engine and the assets as a singleton class. Has anyone ever used a singleton class before? A few people? Okay, so like half the class. We'll talk about whether or not I make this a pointer or a singleton or whatever, but that'll be only important when it comes to the implementation, and I'll show that in the code when I give the assignment 3 lecture. But the basic theoretical properties is all the same. There'll still be a game engine class, there'll still be an assets class, but how we actually access that will be, that implementation may be different. So we can see over here that in order to do this, we have some new variables. So we might have a scenes map. So the way I'm going to be implementing this, because maps are super easy to use and to visualize in your head, we're just going to have a map from strings to scenes. And so, for example, this will be the gameplay scene. So we'll call it gameplay, and then it will store a shared pointer to a scene object. And in order to get the current scene, we might have a variable called scene here, which is a string. So several different scenes might be like actually living in memory, but the current one that we're drawing is this one that we've stored there. So we just have a string, that's our current scene, and in order to get access to that, we just look it up in this map. Just really basic stuff. Also, we may have this assets variable here, which is stored by the game engine class, which just stores all the different assets. And I'll talk more about assets a bit later. Then we will have functions like change scene, so I can change to a different scene at any time. I could get the assets, I could do the user input, etc. Now, the scene class, again, we're going to have this base class of scene and then multiple derived classes, but there is functionality unique to the scene. There's functionality of a scene that every scene is going to want to implement. So we'll implement that functionality in the base class, and now all the unique functionality goes into the derived classes. So the scene base class is going to store the common scene data. So for example, we just said that every derived scene class is going to have its own entity manager. So why don't we stick the variable for that in the base class? Like every scene is going to have an entity manager, so rather than duplicate a bunch of code, the entity manager just goes in the base class. So each derived scene has its own. Something else we may want to know for multiple different reasons is like how many frames has this scene been active for, right? And so the frame counter, maybe some different actions that are relevant to this scene. The whole next lecture is all about actions. And so this is going to store data that should be common to different scenes. So over here, we might have a pointer to the game engine. We have an entity manager over here. We have the current frame and how many frames have passed. We're going to talk about this action map, which maps different things to things. That's the whole next lecture. But basically, the scene base class stores all of that. And so the functionality that's unique to a given scene, so for example, the stuff that happens only in the menu, the stuff that happens only in the playing of the game or the battle scene, that's all carried out in the derived classes of this class. And so the base scene class is abstract, and it cannot be instantiated. You've all talked about abstract classes before, right? So we can never actually instantiate the base class. And the way that we physically do that, the implementation of that in C++, is by defining some functions as equals 0, and that just means this can never actually be implemented. So the virtual function in the derived class, once that is there and it's non-zero, then we can actually instantiate that class. So that's how that's actually implemented. And we have a new function here, which is called simulate. Maybe it's a bad name, but essentially what simulate does is it calls the derived scene's update a given number of times. And the reason for that, as we'll find out later, is we may want to do something like call the game's physics update multiple times before we call the rendering function. And this is just a one function that we can use to do that. And all of this like do action and register action, that's stuff that we'll talk about in the next lecture. The scene derived class, this is storing scene specific data. So for example, the level that we're in, or the pointer to the player who's currently playing, or some configuration file that's unique to that scene. That's what's going to be stored in the derived class. So anything that's scene specific is going to be in the derived class. So for example, we're going to have a scene play. That's the scene where we're actually playing the game, running around in the game. We'll have another one, which is scene menu, etc. So some scene derived classes may require quite different systems based on functionality. And so we will have something where, like, we'll have a physics system which sort of lives outside of the derived class or the derived classes, because the physics is going to be maybe the same in different scenes. So whenever we have a system that could be shared across multiple scenes, we'll just define that sort of on its own. But any scene that's, or any system that's unique to this scene is going to be in the derived class. Update, rendering, do action, they're going to be implemented on each scene. And we'll get into the details of that when I explain it. I know this is sort of a big information dump. Don't worry if you don't understand all of this right now. I'm just giving you the big picture for assignment 3. How would we switch scenes then? So the game engine is going to store a map from strings to shared pointers of scenes. And it's also going to store a string, which is basically just the current scene. And so current scene looks up the currently active scene in the map and then calls its update function. Change scene, it's going to take in a string and a scene, and that's going to change to the new scene or a previously stored one. So for example, let's say we have an inventory menu scene, right? What this is going to allow us to do is, if we're in the gameplay scene and we switch to this like entirely new inventory scene, that gameplay scene still lives in the map, but while the inventory screen is active, essentially that other scene is paused, right? So we can store multiple different scenes, but only one of them is being updated at a given time, so that when we do exit maybe the inventory scene, we're back exactly where we left off in the gameplay scene. And we don't have to like store that data somewhere else. So you can imagine that if we didn't have the ability to store multiple scenes at once, if we created a new scene, like an inventory scene, then our gameplay scene would be like destroyed, and how would we know where to go back to in that level and stuff? It would be really complicated. So that's why we're able to store multiple different scenes in this map. And this is basically, this map is just going to mimic a finite state machine, which I'm sure you're all aware of. So, okay, I'm in this scene, I press this button, it transfers me to another scene. These are basically just states in a finite state machine. So here's an example. So let's say when the game engine is constructed, we're going to have this change scene function, and that is templated. And it's templated so that we know which type of scene that we want to change to. So this might say change scene to the menu, right? So what we would do here is we'd pass in menu as the string, and then any arguments to that constructor, if there are any. And then we just see scenes menu equals shared pointer to scene menu with its arguments. So it couldn't be easier, right? We just call this function change scene, we give it a name, any arguments for that scene. So for example, an argument might be the level that we want to play or something like that. And that just stores it in the map. Then the player is presented with that menu scene because it's currently the only one that exists. But then on the menu scene, let's say we press a button where we select the level, then what's going to happen is the level path is the currently selected menu item, and the menu tells the game engine, okay, now we're going to change scene to the play scene, call this play, and give it the level path, right? And we can change scenes back and forth by doing this, just calling the game engine's change scene function. So again, just like the other instances where we were using maps for things like this, if we were trying to make things as efficient as possible, we would probably replace our map that maps strings to scenes with like a vector that's indexed by some like enum integer with scenes in it, right? So we're not being as efficient as we possibly could, but if you think about it, we're only calling this map every time we want to change a scene. So the overhead of calling a map once every time we change gameplay modes, it's such a small overhead that we're just going to leave it like this for now. Okay, so that's how we're going to store scenes. And I know it's a lot to take in, but we'll get more used to that when assignment 3 rolls around. Let's talk a little bit about asset management now. And assets, the word asset can mean different things when you're talking about different contexts. Like it could mean money to an economist or whatever. But assets in the context of this course are going to be external files that are loaded into memory to be used in the game. So the only file that wouldn't be an asset would be like a config file, right? So something that we've written like that. But assets in this game are going to be textures. So these are going to be literally just image files that I give you with the assignments. They can be PNG files or JPEG files. For the purposes of this course, we're going to be using PNG files. The reason for that is because they're lossless. So they are compressed, but they're lossless compression, so they maintain all of their quality. But even more importantly, the PNG files can support transparency, right? So all images have to be rectangles, but not all the things we want to draw in the game are just rectangles, right? So what we'll do is we might have Mega Man or Mario or Link or Zelda or whatever be in the middle of a rectangle, but all the pixels of that image surrounding them are transparent, so that only they get drawn to the scene. So that's why we're going to be using PNG files. We will also have animations, which is sort of the second half of this lecture that we'll be talking about, but animations are essentially a texture file with some extra data that defines how we want to view it. So that's what an animation is going to be. We're actually not using sound files for assignment 3, but we will be for assignment 4. But sound files for this course are going to be what is supported by SFML. Last time I checked, MP3s weren't supported by SFML because they have some licensing issues with them. But we will be supporting WAV files and OGG files. OGG is some open source audio lossless format. So WAV files, typically, we would use a WAV file for like a shorter sound clip, but an OGG file for like a background music file, because WAV files are uncompressed and they're very large. And so you wouldn't want to have like a 3-minute background song in WAV because it'd be like 30 megabytes or something like that. And also fonts. So fonts are another thing, whereas before in assignment 1 and assignment 2, we were just saying, hey, load this font. Now we're going to store this in our asset manager. And the key mantra that I literally want you to repeat to yourself whenever it comes to video games and assets, load once, use often, right? I'll get to your question in a second. So for example, if we do have a texture of like a bird flying in the sky, but in one part of our game, we want to have like 1,000 birds on the screen, all of those birds should reference the same loaded texture, okay? We're not loading the same file from disk 1,000 different times. We are loading it once, and then we'll have a function to get a reference to that texture. And then that's what we'll be using. You had a question? Yeah, so the question was basically like, do we need to worry about copyright for the purposes of finding assets for the final project? I think we're pretty well covered for like educational use here. You're not going to take your assignment and go sell it because I've copyrighted the code that I've given you. And so as long as you're not trying to like use this for monetary gain, I've never ever had a problem with it, right? I'm literally giving you textures from like Super Mario here for educational purposes, okay? So as long as we add that and you're not planning on selling your game, which you're not allowed to anyway, then we're fine. Yeah, but good question. So how we're going to manage this? Again, we're going to make a little class for this. So we're going to load assets that are defined in an external configuration file. So I'm trying to drive home this idea of data-oriented programming. Wherever there's a variable, we would love it to be in a config file if it's possible to put it in a config file, right? So these assets are one way to do that. I'll get more into the details of how we're going to do this with the assignment when I go over the README file, but essentially we'll have a configuration file with one option per line, just like we did for assignment 2, and we're going to specify things like, hey, load a texture. Give that texture the name Mega Man, and here is where that texture lives on disk, right? Another thing, hey, load a sound. That sound, give it the name Mega Death, not the band, but like the death of Mega Man, I guess. And here's where that sound lives. And so we're going to specify this, and you'll do the same thing for your project wherever you've downloaded your own assets. You're going to specify all of your assets here. And then the asset manager is going to look through that and say, oh, was the first thing on the line texture? If so, load a texture from here, etc. Then what we can do is we can reference that asset via the name that we gave it in the file, right? So if at any point I want to draw Mega Man, I'm going to say assets get texture Mega Man. And then this is going to return a reference to that single texture that I've loaded. And I'm never going to load that texture other than right at the beginning of the game. Similarly, if I want to play a sound, I'm going to get a reference to that sound. And this has a couple of different benefits. One is the fact that we're only loading it once and using it multiple times. But another benefit is that storing these things in the assets class gives it a lifetime, the assets lifetime, as in how long it is loaded into our program, is now tied to the lifetime of the game engine. And I'll give you an example of why that matters in a minute. And so to implement this, we're just doing maps all the way down, right? Because they're easy to use. No, they're not the fastest thing, but they're fast enough for this course. So we're going to have multiple different maps, one for textures, one for animations, one for sounds, one for fonts, and we'll just have mapping from string to the type of thing that we want to load. So over here, we'll see here, we're going to have a map from strings to textures, from strings to animations, strings to fonts, etc. And so this lives inside the game engine class. It may not... Okay, so let me explain this. There's a design and implementation decision to be made when it comes to your assets. It mostly, theoretically, it's all the same, but it differs when it comes to the actual implementation and what your line of code looks like, right? So I'll get into more about what a singleton is later. But the point is, do you want to have the assets class be a member variable in the game engine class? And in order to access the assets class, you'll now have to have somehow a pointer to that game engine class in order to get at the assets. Or would you like to have the assets class be a globally accessible singleton that you can access from anywhere without needing to know where it lives in the game engine class? There are deep debates on this, believe it or not. In our class, the only way this will matter is like the line of code, right? So when I said here before, assets get texture Mega Man, you might see assets instance get texture Mega Man, right? But the real difference that matters is that, is it a globally accessible singleton object, or is it a member variable inside the game engine class? Which one, I kind of go back and forth on which one. Maybe this year I'll use a singleton, maybe not, but by the time I give you assignment 3, I'll have decided on that. There are actual pros and cons to this, but yeah, I'm not exactly sure yet. But these slides assume that it's a variable within the game engine class. So this is going to be initialized inside the game engine's init function. So where we load assets also matters, right? So the most important thing is that we load them before we want to use them, right? Because we wouldn't want to be like in the middle of gameplay and then we're about to see this fish for the first time and we have to load the asset from the file when we scroll over to see the fish. Or the first time we fire a bullet, now we're loading the bullet. Imagine every time we shot a bullet, we had to load the texture from a file, right? That would be insanely slow. Disk access is really, really slow. So what we're going to do is, because our games are so simple and the assets are so few and they're really small file size, like maybe just a few megabytes, even including the sounds, we're just going to load all of our assets when the game engine is initialized. Even if those assets are not all going to be used right away, we're still loading them right at the beginning. So you've all played a game where it's like loading, please wait, right at the beginning. You know, modern AAA games might take a minute on some hardware. You load up GTA 5, my God, you cook supper while it's loading sometimes. But that's what it's doing. That most of that is the loading of gigabytes and gigabytes of assets into memory. However, those larger games that do have gigabytes of access, sometimes, if you go from one place and walk through a door, you might see another loading scene. And so the design decision that they've made is that we're only loading the assets that are going to be used in this place, right? So of the 10 gigs of assets which is actually probably small for a modern AAA game, we're only going to load 500 megs of those because those are the, while you're in your house in like a Zelda game, we only need to load these chairs and this texture or whatever. As we're loading out, there's a little black screen that's loading the stuff that's outside the house. But because our game is so small, we're just loading all the assets at once. So that's another decision you want to make is, do I want a possibly longer loading time at the start? Do I think our users' machines have enough RAM to hold everything? Or am I going to have individual loading scenes where I load the assets individualized to those scenes only? So we're just going to load everything. And what this is right now on these slides, the access to the assets class is inside each of our scenes. We are going to have a variable that points to the game engine. So the game engine stores all the scenes, but the scenes are also going to be given access to some of the data of the game engine, so I can do things like give me the window, give me the assets, stuff like that. The assets are going to be loaded once at the beginning of the program, and then they can be used in any scene. But just, it's so important that they are only ever loaded and initialized once in memory. And I just talked about this. You may want to load assets per scene for larger games. So for example, loading screen, I already talked about that. I forgot that I had a slide that mentioned it. But inside our assets class, we are going to have these variables that store these maps from strings to asset types, and then we're just going to have functions for loading those things, so adding a texture from a file, and getting textures once they have been loaded. Okay, so we've been talking, we mentioned animations a couple of times, and animations, for the context of this course, are going to be what we call bitmap animations, or I think in some place they're called raster animations. But it's essentially a sequence of images that plays at some rate of speed that we are going to define, that when played back at that speed looks like it's animating, it looks like motion, right? So like modern films, if you go to the cinema, most films for the history of film, does anyone know what the frame rate of most motion picture films is? 24. Yeah, so it's actually pretty low. But the funny thing is, if you had a computer or a game system that played games at 24 frames per second, you'd chuck it out the window, right? Everyone, is used to 60, 120, 240 frames per second now. The reason that we can get away with it with like actual movie cameras and movies is because there's like motion blur and we don't actually notice the time between frames. But there's no motion blur for a 3D object or a 2D thing, right? So modern games, yes, modern games can introduce this like terrible motion blur that I always turn off anyway in order to try and, if your game is playing at a lower frame rate, it can trick you into thinking it's smoother than it is, but I always turn that crap off anyway. So there's no motion blur, there's no anything, like however many times this is animating per second, that's going to be our frame rate, and we are going to be defining that frame rate not in terms of frames per second, but in terms of how many game frames need to pass before I want to play the next frame of animation, right? Okay, but first let's talk about what these things are and specifically with respect to SFML, how we use them. So what is a texture? A texture is a graphic, so like some image file stored in some format that is somehow being mapped to some shape, right? So if you play any video game ever, all of the like clothing that the characters are wearing, everything is a texture. And if that is a 2D game like this, then the texture is being mapped to a rectangle. And it's the simplest possible case of a texture. Just an image file, you're mapping it to a rectangle. But if you've got a modern 3D game, you might have a texture that's mapped to like some hero's bicep, or the pants are like have to wrap around a 3D model. If you actually open up the textures that are mapped to 3D shapes, they look all crazy, like a Picasso painting, because it actually has to fit to 3D geometry. But we're dealing with the easiest possible case. Textures can be generated dynamically, right? So for example, I showed in assignment 2, the background of my assignment had a little checkerboard pattern on it. That could be considered a texture. But I was drawing that, I was procedurally generating that texture. by drawing a bunch of different squares on the screen. But they can also be loaded from a file, or sort of static textures, right? So yes, there's an entire world of computer science and game programming that deals with dynamically generating content, or procedurally generating content, or PCG, but that's not what we're going to be dealing with in this course. All of ours are going to be bitmap images. Now, it's a bit weird to say because there is a literal BMP type of file called a bitmap, but bitmapped images just mean that some color data is mapped to an individual pixel in whatever format that you're storing. That's a bitmap. And a rectangular shape with a texture attached to it is typically called a sprite. And then those sprites are going to be drawn to the screen in some fashion to create our game. Sprites are very, very common in games, and older computers, because they had such limited graphical memory, they could basically just draw like what was on the screen, like however many colors. So however many pixels you have, and however many colors you can draw per pixel, that was basically the entire video RAM that you had, and you had to deal with that. And if you wanted to draw like animating sprites, it was so difficult and so memory consuming at the time that computers started introducing sprite hardware. So like Commodore 64, the NES, those older systems, they actually have a physical limitation to how many sprites can be drawn on the screen. So if you've ever played an older NES game, for example, and the sprites start flickering on the screen, the reason for that is because the physical sprite limit has been reached. Maybe I can only draw 8 sprites to the screen at a time, but now there's 16 enemies on the screen. So what's actually happening is those sprites are being loaded and deloaded, like they're alternating which sprites are being drawn. So like on one frame, you're seeing 8 of them. On another frame, you're seeing another 8 of them, and they're going back and forth. So it was a real like problem. Like memory used to be a problem. We're very spoiled these days with how much RAM we have. And at the very end of the lecture slides, there's a video called like How Old School Graphics Worked, and it talks about this, and it's really interesting. And it actually shows how like Pac-Man for the Commodore 64, like the code of the game has individual lines of code where you are setting the sprite value in lines of code, in hardware, in your game's code, right? So it's not loading a PNG file. No, you're programming the sprites. It was crazy. So it's a cool video to watch. That won't be on the exam though, just to let you know. So in SFML, this is from the 2.5 tutorial, but it's fine. It's the same thing. If we want to know what a sprite is, a sprite in its SFML implementation is a lightweight object. When I say lightweight object, what that means is it's only got the data that it needs and no other data. So if we take a texture that has been loaded somewhere into memory, and we have an entity, or in this case in SFML, it will be like an int rectangle, so a shape. We take a shape, map that shape with a texture, and we get a sprite. That's what a sprite is going to be. And, oh, I thought I had a, where do I have this? Okay. I thought I had code here that showed you that a sprite inside SFML, if you actually go to the GitHub and look at the source code for a sprite, what it stores is a shape. So it's got this rectangle shape, and then it's got a pointer to a texture that lives somewhere. And that's it. The sprite doesn't store the texture. If we have 500 sprites, we don't have 500 textures. We just have 500 pointers to those textures. So creating new sprites in SFML, those are all lightweight objects. Those we want. So we'll load the texture once, and then we'll create new sprites with those textures so that we're not duplicating the texture data. SFML, luckily, knows a bunch of different common image formats, and we can just load textures from files. So here, texture.load from file image.png, now we have a texture. And the loading, this might be open from file in the new version of SFML, apologies. The loading of anything from a file returns a Boolean of whether or not that file was loaded successfully. So if we didn't load that successfully, here is where we would throw some sort of error or handle that exception. Okay, sorry, the English meaning of exception, not a programming exception, because this doesn't throw an exception, it returns a Boolean. We could, if we wanted to do some procedural content generation, we can manually generate our own textures. And we can texture.create, and this will create a new texture of size 200 by 200, and then we could set the individual pixels of those textures if we wanted to. So if you are interested, maybe you do want to do some procedural content generation for a bonus part of your project or an assignment, you can manually construct the, you can get as low level as you want, right? Rather than just loading from a file, I can say, okay, here is my uint8 data that I'm storing. So this is the actual color pixels that I'm storing manually. I can update a texture with those pixels. I can have an SF image that I load that I set the pixels from. Or I can take a texture and take a window contents and create a texture from those window contents. So for example, if you wanted to like save a screenshot for assignment 2, you would take a texture, grab the screen contents from the window, store it in a texture, and then write the texture out as an image file. And so you can do all sorts of crazy stuff with textures. Something that's really interesting, and we'll get to this more in a bit, is that sometimes the texture will not be the same size as the entity's actual shape, right? And also, the texture might contain a lot more data than we actually want to draw on the screen at any given time. So one thing that we can do is when we load a file, we can specify a subrectangle of that image file to load as this texture. So this is just a helper function that SFML has built in, where I could say, okay, I know there are actually 4 or 5 different characters in this texture, in this image file, but I only want to load this one, right? So that's one way to do it. I'll show you in a second another way to do it. So sometimes the texture will not be the same size as the entity's shape. So what do we do here? Like, okay, the Mega Man texture is not the same size, or the image file is not the same size that we want to be drawn in the game. If we resize it, maybe this could affect gameplay somehow. If we resize the texture, that could be really expensive. We don't necessarily want to do that. So what we can do is whenever we have a texture, when we go to draw the texture, we could, so by default, if I draw a texture to the window, it just draws the whole thing. But what I can do is instead of just loading a sub-region of that texture from the file, I can load the whole texture and then just draw a subtexture. So this actually has benefits like on the GPU side of things. You just send it the whole texture and then say only draw this sub-region versus here's 1,000 different textures and draw the whole thing of different textures. And so the entire texture is still loaded, but not all of it is drawn. And this will make sense why we would want to do this in a second. But just keep in mind that this is what's happening. We're loading some texture from a file, or we've created some texture somehow, and then we are going to specify some rectangle within that texture to actually be our sprite that we draw to the screen. So here's an example. Let's say we wanted to do animation, right? And we didn't want to have a different image file for each frame of the animation. Now, just to let you know, the word frame is about to be said a lot, and it's a bit of an overloaded term. So there's a couple of different things frame means. In this case, a frame of animation means this, and then a new frame is this, right? Another frame is going to be the frame of the game that we are currently on, right? So if the game is running at 60 frames per second and the game frame is frame 240, then we are 4 seconds into the game. But we could also say frame to mean I am currently playing the first frame of animation, the second frame of animation, the third frame of animation. So just keep in mind that that's going to differ depending on the context. So something we might want to do is have an animation, all the frames of that animation be defined in a single texture, right? That way, when I tell my graphics card to, hey, draw this frame of animation, I don't need it to like context switch to a different texture, right? I can just say, draw this subregion, and I've defined this within the context of my game to be 1 frame of animation. Next, hey, you're still drawing the same texture, but now you're drawing this part of it. Next, you're drawing the same texture, but now you're drawing this part of it. And then it would go around back to the start. Okay, so that's the context for why I might want to actually draw subregions of the same texture. So in SFML, how do I create a sprite? I can create a sprite and then set its texture. Really, really easy. And then I can just window.draw sprite. The only other thing you would need to do is set the position of the sprite, right? So I've created a sprite. The sprite has a texture. That does not copy the texture data. It just points to the texture data within the sprite. And then the sprite is going to have some other properties on it. So for example, maybe a rotation or a position or a scaling value. It's storing the lightweight stuff. So in SFML, the way we do this is by saying sprite.setTextureRect, and then we pass in an integer rectangle. The rectangle, so for example, 10, 10, 32, 32, this would say go over by 10 pixels and down by 10 pixels, and then take a 32 by 32 pixel rectangle of this sprite. So this one here would take like the middle portion of this if we called this. It would be a square of size 32 by 32 taken from 10, 10 within that image. So that is how we would set that textured rectangle. Oh, here it is. Okay, so this is my slide on it. Sprite is a very lightweight object. It consists of the vertices, the texture pointer, and the rectangle from within the texture that we actually want to draw. So the vertices, that defines where on the screen the 4 vertices of this sprite are, because we could transform a sprite, right? We could take a sprite and rotate it, we could zoom in on it, we could scale it, and so these vertices are what is sent to the graphics card to say, we are going to be drawing this subrectangle of this texture to these 4 vertices. And then the graphics card will figure out how to do that for you. But be careful. Sprites store pointers to textures. So when I mentioned before about the lifetime of assets, those matter a lot. And here's the example why it does. So let's say I want to load a new sprite from a file name, for example. So this function, let's say I'm going to pass in Mario and I give it mario.png. This function is going to fail spectacularly. It looks right. Theoretically, it is kind of right. But why doesn't it work? Well, in C++, the reason is we've created this stack allocated variable, right, within this block of code. We then load a texture from this file name. That texture data lives on the heap somewhere that's referenced by this texture. Now, what I'm going to do is create a new sprite object with this texture, but what does the sprite do? It just stores a pointer to the data of that texture. As soon as this is returned, this block of code exits, and what happens when we exit a block of code in C or C++? All stack allocated variables that were created in that block of code are now destroyed. So their destructor is called, it frees all the memory of that texture, and now we have been returned a lightweight sprite object with a pointer to nowhere, right? Whatever happens to be in memory at where that texture used to be is now what this sprite is referencing. And this, depending on how good your compiler is, may or may not give you a warning, right? I have had this happen and beat my head against the wall until I realized what was going on. So what the assets class does for it is the assets class lives for the entire duration of our program. So you start the program, it loads the assets, and then it lives until the game engine is destroyed. So if we did create a load sprite function now, that would load from our assets class, which would not be destructed when this scope of code ends. So it is guaranteed to be pointing to some place in memory that still exists. And the same thing can happen for sounds as well, because the sound data is loaded, and think of the sound data just like the texture data, right? So in SFML, we'll only be doing sounds for assignment 4 in the project, but the sound data is called a sound buffer, and that's where the data lives, like all the actual frequencies and stuff. Then there's a sound object that is a lightweight object that stores a pointer to the sound buffer, as well as the volume we want to play it at and where we currently are in the sound. So if you load a sound buffer from a file, then return a sound object in the same way, it won't be living as long as you think it is, and the sound object will no longer play. Okay. Let's say, oh, yeah, you have a question?
Yeah. How would that work that's too big to feed?
So your assets class would just be like in the scene instead of in the game engine. So your assets do need to live for the duration of however long you need them, no matter what. So you have to architect a solution that guarantees that. Yeah. So sometimes you could have games like, God, there's this amazing, amazing video of the person who was one of the programmers on the Crash Bandicoot for the original PS1. And they also had to deal with assets that were on a CD spinning that were in certain blocks of memory that took forever to load. And they were like streaming assets and predicting when you'd need assets and loading them from then. And then if you'd pass them, they were unloading them. And it was like, however you get it to work is fine. But this can be like PhD thesis level intricacy if you really wanted to, right? But for our game, luckily, we just load everything. But the real answer to your question of how you manage that is pretty much you'll define some high-level concept of an area in your game, and then ensure that all the assets for that area are loaded, and when you leave that area, you may deload those assets and load the assets for the new area. So whether that's like an old PlayStation spinning disc, loading, please wait, don't turn off your game, or if you're getting close to an area in like World of Warcraft where the whole game is like, there are no loading zones in the outside. Maybe now, okay, I'm getting close to this area, so I'll load the assets for that area, but I won't have the assets that are on the other side of the world loaded, right? So like in games like that, in massively multiplayer games with huge maps, typically what you'll see is as you're running around the world, there are no loading zones, but if you teleport somewhere, there is a loading, right? Because it's this stuff that's way over there that I didn't think I would need until I actually teleported there. So that's just ways that you get around that. Okay, let's say in our game, we load this like gray circle or whatever. But we would also want that circle to maybe be blue because it's a snowball in this scene, but maybe it's a lava ball in another scene and we want it to be red, right? So we don't need to go create assets of all of those different colors. We can take a texture and sort of plaster a color on top of it. So I can set the color, if I load something in an initially neutral type of color, then I could set the color of that thing with sprite.setColor. Okay? So by setting the color and messing with its transparency and its color values, we can actually apply different colors to sprites. Now later on in the class, when I get into the shader lecture, it's probably the case that if you want to be efficient with this, you would use shaders. But as a quick and dirty thing, you can set the color of something. Just be careful that when you set the color of a sprite, it's almost like an additive color, as if you'd taken two transparencies and put them over each other. And so if you have a green thing, or so let's say you have a blue object, and you set its color to yellow, what it's actually doing is like taking yellow and putting it on top of the blue, and now your thing is green. Whereas you said set color yellow, it doesn't actually make it yellow. It adds yellow to the current color. So that's why this may not be what you want. Also, I'm sure you've all used some sort of Photoshop or Paint or whatever, when you zoom in and out on an image, whether or not you want that image to be like smoothed or not, or still be pixelated or not, that is controlled by setting the smooth variable on a sprite. So set smooth false, what that will do is, like, let's say I have an image that's constructed of pixels, like Mega Man, like blocky type of art. If I zoom in on that by like a factor of 8, then all the pixels will still be very clearly visible. They'll just be 8 times larger. But if I set smooth to true, then what's happening here, you see the difference here? This one maintains the blockiness, but this one tries to apply some sort of smoothing or blending to it. So that's the way that's done. And the way this is done under the hood is with typically it's a procedure called MIP mapping. And MIP mapping actually takes a texture and loads it at different resolutions. And then, and that's all handled by the graphics card. But if I want to draw it at this larger resolution, it'll take the version that's larger and draw that one, rather than on the fly trying to zoom in and do all that math. You had a question? Oh, okay, perfect. Also, something that you might want to do is, let's say I have a big brick wall, and I want that brick wall to be textured like bricks. Now, would I have to create a texture the size of the wall and load it onto that? Well, that depends. If I want, I could have a tiny texture and set repeated. So what set repeated will do is, in this example, I might have, this is the actual texture. Okay, it's right here. So if I take a sprite that is larger than that texture, if set repeated false is on, it will zoom in on that texture and stretch the texture to match the size of the sprite. But if I set repeated to true, instead of stretching the texture to match the sprite size, the texture will stay its size and just be repeated in the X and Y as a repeating pattern. So we could take a wall, have a little texture of a brick, and just have it be repeated for us. Question?
Does your sprite have to be like a multiple of the texture size?
No, so it will stretch it like, so the question just for the mic is, does the texture have to be a multiple of the sprite size? Or the opposite? Yeah. So if, for example, you load a texture and set it to a sprite that's twice as big in the X, it'll just stretch it and it'll look terrible. And if you have a sprite that is way bigger than the texture with repeated, and it's not an exact multiple, it'll just cut it off in the middle of one of the texture repetitions. So it won't be like white on the end, but there's options for all of that, right? So you'd be able to set that. Lots of different transformations on Sprite. So once it's set up, you can set its position. That sets its position in the game world. So then that's where SFML will draw it. Its rotation as well. You can rotate, scale, all sorts of things on sprites. Oh geez, I'm running out of time. So I really gotta speed up here. Texture sheets. Games can have many textures. And it can be hard to manage that many files. So what games did back in the day, and still do, is have a texture sheet, which is a bunch of different textures in the same image file. And so the entire sheet gets loaded into graphics memory, and then we just say, I want to draw this subtexture of that. So if I want to specify an animation from this one sheet, I would say, this is the first frame, this is the second frame, this is the third frame, etc. Lots of texture packs out there for different types of games. If I wanted to make some sort of Farmville or Stardew Valley, I'd download something like this and just play it like that. And what this does is it makes it so that the GPU can load this one texture, and then I just specify the rectangle that gets drawn. So instead of loading a different texture for everything, you just figure out which sub-rectangle you want to draw. Rectangles can be stored as variables or computed dynamically if you want to. And so here, for example, this is the left, top, width, and height. That's how we specify that rectangle. But the most important part of this lecture for assignment 3 is, finally, the texture-based animations. So animation is a sequence of images that, when played, looks as motion. Texture animation can be achieved by quickly displaying different textures. And there are, again, an infinite number of different ways to do this. I'm just showing you one that is a nice balance of being easy to implement and fast enough. So bitmap animation is equal, sorry, they're two terms for the same thing, bitmap or raster animation, made of pixels rather than vectors. So assignment 2 was done with vectors, meaning we were drawing lines, now we're drawing bitmaps. How do we implement it? Okay, So what we're going to do is, instead of having a 2D sheet for our sprites or for our textures, what I've done is, in assignment 3 and 4, I've created one-dimensional thing, just so the math is a little bit easier for you. So every animation that we have is guaranteed to be 1 frame tall and n frames long. That texture is going to have some width, meaning the entire image file is going to be some width, and the height is going to have some height. The texture width may not be the same width as a frame of animation, because there might be multiple frames, but the texture height for this class will be the height of 1 frame of animation. In this example, there's going to be 3 frames of animation. So what we have to do is figure out what the frame width is, and that's pretty easy. It's just going to be the texture width divided by the number of frames of animation. And I'm guaranteeing you, for this class, for the assignments that I'm giving you, it will be in this format. So if it's, 64 pixels wide and there's 3 frames of animation, then the exact width of the image file will be 64 times 3. I'm guaranteeing that that's going to be the case. When it comes time for you to make animations or whatever for your project, you're going to have to specify that as well. So the rectangle that I want to draw has to have the coordinates, the x value of the left, the y value of the top, the width, and the height. Luckily, the y value of where we want our rectangle to start is always going to be 0, because all of our animations are just like across like that. So the top left corner is always going to have the y equal to 0. That's why I have this here. And then I'm going to figure out the frame width. So that was the total size divided by 3 in the last example. Then I multiply that by the frame that I want to draw, and that's where the top left corner of the rectangle is. Then the dimensions of that rectangle are just going to be the width of a frame and the height of a frame. And the height of the frame is the height of the texture. So let's look at an example. Let's say I have figured out FW and FH, because that's just given to us. If I want to draw frame 0, that's going to be frame, which is 0, times FW, so that's 0, 0. So we start in the top left corner of the texture, and then it's frame width over and frame width down, right? Frame number 1, that's 1 times frame width, so that's frame width, so it starts here, and it goes down to here. Frame 2, frame 3, 4, 5, etc. So that's pretty intuitive. In order to implement this, we have a class for that, right? That should be sort of the slogan of this course. It's going to store all the variables related to the animation. And we're going to have an update function on that class to provide logic to progress the animation as we want to. And so cAnimation, that's going to be the component, and the component is going to store this animation variable. Now, this is a very slight departure from our architecture of components being pure data, but trust me, it's for your own good. Having an animation class that does this for us, instead of having to create an animation system for every different scene, is going to save us a lot of time. So that's why the functions are on this animation class. But we are still sticking to our guns. There's no functionality on the component itself, just on the animation class that it stores. It's going to store some variables. It's going to store a frame count and a game frame. So frame count, I'll get into what these mean in a second. It's going to store a size. So the size is going to be the size of 1 frame of animation. So that's the texture width divided by the frame count. So frame count is the number of total frames of animation that are specified in this. And then the game frame, that's going to be the number of game frames that this animation has been active for. So if our game is 60 frames per second and this animation has been active for 2 seconds, game frame will be equal to 120. All right. We're also going to have a variable called animation speed. This could be called animation speed or animation duration. But what this variable means is that, let's say animation speed is set to 10. It means that every 10 game frames, we're going to go to the next frame of animation, right? So if animation speed is 10 and our game runs at 60 frames per second, 60 divided by 10, that means we're going to be showing 6 frames of animation per second. And you'll vary this to look as good or as bad as you want in your game. So what's going to happen on each update of the animation is we're going to increase the number of frames that this animation has been alive. We're going to determine the animation frame that should be played. How? Well, it's just the game frame divided by the speed, right? So if I'm on frame 100 and it's a 10 speed, then I should be playing animation frame number 10. But what if I only have 3 frames of animation? Well, we've set up the animation so that it goes frame 1, 2, 3, and then back to the start. And so if we want something to wrap around, we use modulus. So it's modulus the number of frames, right? So if we have 5, if this variable here, if the result of this division is frame 5, but we only have 3, 1, 2, 3, 1, 2. So we'd currently be showing frame number 2. The rectangle, that is the animation frame that we should currently be playing times frame width, 0 frame width, frame height. So that's the math that we just did. And then all we have to do is take that sprite that's already pointing to this animation or this texture and set the rectangle that we want to draw. And then on the next frame, you're drawing the animation, you're drawing the sprite of the animation, and it will look as if it is animating for you. So this is just one way to implement this, but it's going to work pretty well. And it turns out that Mega Man actually has 4 frames of animation for our assignment. So he's like running and then not, and then running and then not. Now, if you wanted to, there's all sorts of ways you could do this. So for example, there are only 3 unique frames of animation here, right? So what we could do, if we really wanted to save space, like back in the day when we only had a few kilobytes of memory, we could say, draw this frame, then this one, then this one, then this one, then this one, then this. So we could like go back and forth rather than starting back at the beginning. But because I want this to be as simple as possible for you and not have different types of animation, I just duplicated that frame at the end so you can just wrap back to the start because the RAM isn't our bottleneck here. And the way we specify animations in the config file for the assets is like this. So I've loaded a texture, right? So the texture here, this one is going to be called tech run or texture run, whatever string you give to it. And then it's images / megaman / run 64. The reason it's called 64 is because the images I give you are 64 pixels square, right? So this is run 64. It's 64 pixels high, and it's 4 times 64, what's that? 256 pixels wide. And then to specify an animation, I say, okay, my animation called run is going to reference this texture. It has 4 frames of animation, and I want to progress the animation every 10 gameplay frames. And so if I change this 10 to a 5 in my config file, now Mega Man is animating twice as fast. He's not running twice as fast, he's just animating twice as fast. Okay, so that's how we're going to do it, and I'll have more details about that when we get to the assignment. And here's the architecture of assignment 3. You're writing real software now, right? Now, probably 80% of that will be given to you as the skeleton code, and you'll just be writing like the gameplay stuff. But we're actually writing like a pretty neat game engine now. I don't actually have time to show this video now, so please go watch it. These are 2 videos. One is the importance of keyframes and run cycles, and it talks about how, don't leave just yet, I still have something to show you after this. So this talks about how even animations that have very few frames, that doesn't necessarily make them worse than animations that have more frames, okay? And it gives some really good examples. This is the video that goes into things like old school graphic sprites and stuff, which is also very interesting. That will not be covered on the exam. That's just sort of if you're a nerd like me. So the thing that I want to show you is really quickly, this is assignment 3. Let me try and zoom in on this just a little bit. So in assignment 3, you have Mega Man here, and Mega Man is animating. Let me zoom in on this a little bit, and I'll run into a wall. Okay, so Mega Man is standing, looking in one direction. If I press left, he's now looking in the other direction. If he jumps, the animation changes to a jumping animation until he hits the ground. And if I'm running in a particular direction, now he's animating, right? So the logic of your gameplay when it comes to animations is going to be, I'm going to have some sort of state machine that I'm keeping track of somehow, of like the state of Mega Man. So every entity is going to have a state variable now. That state variable is going to be like, am I in the air? Am I on the ground? Am I jumping? Am I not? Am I running? Am I not? And also, another example of animations is if I hit this question mark block, a couple of things are going to happen. I first have to detect that I've hit it. I have to detect that I've hit it from below. And then an animation of a coin is going to appear and then disappear. How is that going to happen? Well, when we hit this from below, and you already know that, how to do that because of the previous lecture, I'm going to change this entity right here into, I'm going to change its animation from this blinking question mark to a blurred out or a darker question mark. And then I can say, if I hit a blinking question mark, I'm going to spawn a new entity, one tile up from it, with this animation, but it has a lifespan. So all I have to do is say, in order to do this complex thing of have a coin spinning appear and then disappear a certain time later, new entity above the block with this animation that I've already specified in the config file, give it a lifespan of 2 seconds, and it's just done for me, right? And also things like, oh, I'm going to hit this brick and it's going to have an explosion. Like, not really true to the original game, but also when I hit the brick, oh look, I can jump through the explosion now. So we're going to talk about adding bounding boxes, removing bounding boxes, setting animations, all sorts of stuff like that for assignment 2. All right, that's it. Thank you.